After a brief review of Maxwell's field equations, today we are going to discuss a most important theorem which is known as Poynting Theorem. In fact, Poynting Theorem is simply the energy conservation in electromagnetic field, and we will discuss this conservation principle in electromagnetic field while dealing with this Poynting Theorem. Actually, we deal with the Poynting Theorem in three conditions. I have just mentioned here all those three conditions under which this Poynting Theorem is dealt in. So the first condition is when the dielectric medium is linear with no dispersion or no losses. When you say that dielectric medium is linear, it means these electric equations are valid. You know D equal to epsilon E, where D is electric displacement, E is electric field, and epsilon is the permittivity of the medium. And at the same time, the magnetic induction B is equal to mu H, where H is the magnetic intensity and mu is permeability of the dielectric medium. When you say there is no dispersion, what does it mean? Actually, dispersion means variation of this epsilon and mu with frequency, and these are in fact complex in that case. When dispersion takes place, then epsilon and mu are not real but complex. So if there will be no dispersion, it means these quantities epsilon and mu will be real and independent of frequency of the wave. And so this is the first condition, which we will discuss the Poynting Theorem. And in this lecture, I would like to discuss this theorem in this condition, that is when the dielectric medium is linear and there is no dispersion and no energy losses. The other two conditions in which Poynting Theorem is dealt is, second number is when the dielectric medium is linear but dispersive with losses. So linearity condition here also holds, but we will consider that epsilon and mu are frequency dependent. And the third one is in case of harmonic fields. When we consider the harmonic field, then what will be the Poynting Theorem? The gist of all forms the gist of Poynting Theorem in any condition is same, that it is in fact dealing with the energy conservation in electromagnetic field, but in accordance with the nature of the medium, its mathematical form changes, but the inner fact of the theorem remains same. So now let us consider the first condition in which we are going to discuss this theorem, that is Poynting Theorem. So first of all, we will discuss Poynting Theorem in this condition which has been mentioned here, that is we will derive Poynting Theorem with a restriction to a linear media with no dispersion or no losses. And as it is a theorem, so at first I would like to state the theorem, and after knowing that statement, we will actually prove this theorem or deduce this theorem, and after its deduction, we will interpret each and every term, and then you will see how this theorem actually is simply the statement of energy conservation in electromagnetic field. So first of all, I have written here for your convenience the statement of the theorem in case of linear dielectrics with no dispersion and losses. What the theorem states, that statement is the time rate of change of electromagnetic energy within a certain volume plus the energy flowing out through the boundary surfaces of the volume per unit time is equal to negative of the total work done by the fields on the sources within the volume per unit time. So this is the statement uh, I would like to explain this statement after the derivation, because when we will derive the mathematical form, then it will be very easier to explain this statement. So let us leave it just as a statement, and explanation will come after the calculation or after the deduction of the Poynting theorem. I have also mentioned here its mathematical form directly, but just in this lecture I would like to derive this statement. In fact, Poynting theorem is stated either in differential form or in integral form. Although meaning of both of these forms will be same, both will in fact represent the energy conservation in electromagnetic field. Only the mathematical form appears different, but the inner meaning or the sole meaning of these two mathematical forms of this theorem are same. So what is the differential form of the Poynting theorem? This in fact is del t half E dot d plus H dot b plus divergence of E cross H equal to minus J dot E. I hope you know the meaning of each and every term. You know E is electric field, D is electric displacement, H is magnetic field, and B is magnetic induction. And this J is actually the conduction current density. Actually, you know half E dot D. In fact, this represents the density of electric field energy, and half H dot B represents the density of magnetic field energy. And so, in fact, this first term in LHS of equation A represents the total energy density in electromagnetic field. And this divergence of E cross H, we will see later that this quantity E cross H is actually denoted by S, and that is called Poynting vector. And here you can see del t operator means what? We are taking just the time rate of change of the total energy density in electromagnetic field, and this is equal to minus J dot E. We will see later that this J dot E is actually the work done by the fields on the charges or on the particles or on the matter per unit volume per unit time. We will see later. I have just mentioned here, but after the deduction we will explain each and every term in this theorem. And this is its integral form, when in fact this result defined in equation A is integrated for a volume V which is bounded by a closed surface S. Then after taking the volume integral of equation A in integral form becomes like equation B. Here only after the application of Gauss's divergence theorem, the integral of divergence E cross H has been changed into a surface integral. The only difference is that. And so these equations defined in A and B actually represent the mathematical form of the Poynting theorem. I have just here mentioned it directly, but now I am just going to derive these two results first of all, and after the derivation we will discuss each and every term in these two equations. So now let us know the derivation of the Poynting theorem or its mathematical form. So deduction, how we will derive this theorem, let us see. Actually, starting from the Maxwell's two time dependent equations, we can derive Poynting theorem. So let us start with Maxwell's two time dependent equations. There is no need of time independent equations, so we will just write only the two Maxwell's equations which are actually time dependent Maxwell's equations. So time dependent Maxwell's equations are. You have already studied in previous lectures Maxwell's field equations, and you know the time dependent Maxwell's equations are. The first one is curl of H is equal to J plus del D by del T. You know this del D by del T is actually displacement current density. Let us say this is equation 1. And the another time dependent equation of Maxwell is what? In fact, that is curl of E is equal to minus del B by del T. You know it. Now, as we have to reach a particular result, so there will be some mathematical steps. So follow the proper mathematical step, and then you will see we will easily achieve the mathematical form of Poynting theorem. So first of all, we take a scalar product of this equation A with E. A scalar product of equation 1 with E, vector E, and that of equation 2 we take the scalar product with minus H. So take a scalar product of equation 1 with vector E, electric field vector E, and that of equation 2 with minus H. And if we will take the scalar product of vector equation 1 with E and that of equation 2 with minus H, then what we will get? This will be in fact E dot curl of H, and this will be J dot E. You can also write E dot J, but you know the scalar product of two vectors is commutative, so there will be no difference between J dot E and E dot J. So both are same, and this will be E dot del D by del T, and say this is equation 1A. Now we have to take the scalar product of equation 2 with minus H. So what will be our result? And there will be minus H dot curl of E, and this will be equal to, as in RHS there is minus sign, that will be cancel out, and our result will be simply H dot del B by del T. Say this is 2A. Now let us add these two equations, 1A and 2A. So we will add these two equations, 1A and 2A. Adding 1A and 2A. When we will add these two equations, see the equation and write it here. This will be simply E dot curl of H minus H dot curl of E, and this will be equal to what? This will be J dot E, see the equation, plus E dot del D by del T plus H dot del B by del T. And you can simplify it. Let us take minus sign common in LHS. So what will be our result? So this will be in fact H dot curl of E and minus E dot curl of H, and this is equal to J dot E plus E dot del D by del T plus H dot del B by del T. We can write it in this way. Now let us see this expression. In fact, this is a vector identity. H dot curl E minus E dot curl H. Actually, this vector identity is equal to divergence of E cross H. So we can write it as minus divergence of E cross H, minus divergence of E cross H, and this equals J dot E plus E dot del D by del T plus H dot del B by del T. And let us say this is in fact equation 3. Now we will simplify these two terms, E dot del D by del T and H dot del B by del T first of all. So to simplify this, let us start with finding the term E dot del D by del T. I am just going to find it. So now let us use a simple algebra here. We can in fact write 2 E dot del D by del T. Del D by del T. And as you know, the dielectric is linear, so we know that this electric displacement D is what? This can be written as epsilon E, where epsilon is the permittivity of the medium. And as we are considering a linear dielectric with no dispersion, no losses, so this epsilon will be in fact in this condition a constant for a given medium and a scalar. So we can take it out from the differential operator. So you can write it 2 epsilon E dot del E by del T. We can write it in this way. Now let us further simplify it. So What was in LHS? That was 2 E dot del D by del T. And this is in fact equal to, see this equation, I have written it in this way, 2 epsilon E dot del E by del T. And this expression can be written in this way, epsilon E dot del E by del T plus E dot del E by del T. Because there is a factor 2, so we can write it in this way. Now see the quantities in a square bracket, and you can see we can write it as del T E dot E. You can write in this way because there is a product of two functions, and if you will take the differential, what will be the result? This will be E dot del E by del T plus second factor E dot plus del E by del T. And again, if we will multiply this constant epsilon with one of the E, because it is a constant, so we can write it inside the operator. So we can write it del T E dot epsilon E. And what will be this? This is actually equal to del T E dot D. Epsilon E is equal to D. And therefore, you can see we can write E dot del D by del T is equal to what? This 2 factor will be here in denominator. So this will be 1 over 2 del T E dot D. And this is 3A. We have just evaluated this term in a particular form. And in a similar manner, we will now evaluate the another term H dot del B by del T. So again, you can write it directly on the basis of this result, but I am just giving again the proper calculation. So again, we have to find H dot del B by del T. But again, I am starting with multiplying it by 2. And so this will be, and you know what is this B? B is actually equal to mu H, and mu is constant, so we can write it as mu into H dot del H by del T plus H dot del H by del T. And see here, you can write it mu del T H dot H. And again, we can take this constant factor mu inside the operator, and when we will multiply this mu by one of the H, that will become B. and so you can see we may write it as, so 2 h dot del B by del T equal to what? This will be del T h dot mu h. We can write it in this way. And you know mu h will be in fact B. So this is equal to del T h dot B. And so we can find h dot del B by del T is equal to what? This is 1 over 2 del T h dot B. And say this is actually equation 3b. Now we have just evaluated these two quantities, E dot del D by del T and H dot del B by del T. Now let us substitute these two values in the equation which is that equation. That equation is equation 3. We will substitute for E dot del D by del T and H dot del B by del T, which we have just evaluated, in this equation 3. And when we will substitute it in this equation, what will be our result? You can see here. So using 3a and 3b in equation 3, what will be our result? Actually this will be minus divergence of E cross H equal to, see the equation 3, that is equal to J dot E and plus, as 1 by 2 is a constant factor, so we can write it inside the operator, and so this is written as del T 1 over 2 E dot D plus H dot B. We can write it in this way. Or this equation may be written as del T 1 over 2 E dot D plus H dot B and plus divergence of E cross H. I have just written this divergence of H in this side, and so that will be equal to what? This is minus J dot E. And see the statement which I have mentioned earlier in equation probably A. See here. This is the statement, and we have just derived this result. But till now we are not knowing the significance of any term. We will discuss it separately. but this result has been derived very easily, you can see. And so this is the differential form of Poynting theorem which we have derived. So I am just again writing it equation A, because this is simply equation A, and you can see the importance or the meaning or the significance of this equation after some time in this lecture. Now, as I have told you, this is differential form of the Poynting theorem. Now, in fact, we want to change the differential form of Poynting theorem into its integral equivalent. And so, for this purpose, I am just assuming a closed surface. Let us suppose S is a closed surface and it bounds a volume V, and inside this surface there are sources of fields, that is there are electric charges which are in motion. You know, electric charge is a source of electric field, and if it is in motion, that will be also a source of magnetic field. So this this closed surface actually contains moving charges, and that is called source of the fields, and it encloses the volume V. So now let us take the volume integral of the equation which I have just derived in equation A. See this equation A. We will just take the volume integral of this equation A for the volume V, which is actually enclosed by the closed surface S. So taking the volume integral of the equation A. In fact, for volume V enclosed by a closed surface S. So what will be our result? You can see this will be integral over V del T 1 over 2 E dot D plus H dot B dV, and plus integral over V divergence of E cross H dV, and this is equal to minus integral over V J cross E dV. Now you can see, in fact, the second volume integral in LHS of this equation, this is in a volume integral of divergence of a vector E cross H. And you know, we can change a volume integral into a surface integral by the use of Gauss's divergence theorem. So if we consider that there is an elementary area dA at the surface S, and in that condition, what the Gauss's theorem states? Gauss's theorem states that the volume integral of divergence of a vector field is equal to normal surface integral of that vector field over the closed surface which encloses the volume V. So using Gauss's divergence theorem. If we will use this theorem, we can write from this theorem that integral over V divergence of E cross H dV, and this is in accordance with this theorem. This will be actually equal to integral over the closed surface S of vector E cross H dot dA. Actually, this is simply Gauss's divergence theorem. Now, we will use this result in the above equation, and so after using this, the second integral, which is a volume integral, will be now changed into a surface integral. So, after using this, the above equation becomes, what will be now this equation? This equation will be simply integral over V del t 1 over 2 E dot d plus H dot b dV, and plus integral over S E cross H dot dA, and this is equal to minus integral over V J dot E dV. And you can see the equation which I have mentioned in the statement of Poynting theorem in equation B. This is simply that equation. So you can see by using the Maxwell's time dependent field equations and some of the mathematical steps, we can easily find the mathematical form of the Poynting theorem. So this is mathematical form, but until we are not knowing the physical significances or the physical meaning of each term in these equations, either in equation A or in equation B, so our next task is to know or to find the physical interpretation of each and every term in equation A and B. And when we will do it, you will see that these equations simply represent the energy conservation in electromagnetic field. But for your convenience, I am just stopping the lecture on the Poynting theorem at this moment, and in second lecture or in second part of this lecture, we will interpret the different terms occurring in equation A and equation B, and then we will see how this statement or how this mathematical form explains the energy conservation in electromagnetic field.